my thesis, I look at optimizing the use of the graphics processor in the context of TV broadcasting. That means I look at generating broadcasting graphics, and I have prepared a short clip and asked my colleague Claudia to explain broadcasting graphics.
Hi! Broadcasting graphics are an essential part of your TV program. A simple example is the station logo in the upper right corner of the screen. Other examples are text messages on top, or a lower third bar which describes what the program is about. During a live broadcast, the editor often needs to make last-minute changes or fix typos. This requires graphics to be generated in real time. There are many challenges when developing a graphics system for broadcasting. The following presentation shows some of the major ones and how to solve them.
Okay, thank you Claudia for the introduction. So, how is this actually done? Where are broadcasting graphics generated? In broadcasting we have the so-called playout stage, which is really the last instance right before the on-air signal is generated. The playout server takes video frames from a file, camera or a network stream. Graphics are rendered by the graphics renderer, which is part of the playout component. Now there are two major challenges in broadcasting for this particular component. The first one is that the input video format very often does not match the video format in which we're going to render. So the images of the video stream need to be converted back and forth between those two formats. This is difficult if you want to keep the quality high, which is a necessity in professional broadcasting. So this is the first one. The second one is the on-air signal operates in a fixed video frame rate. So in Europe, as it is today, video is presented in 25 Hz, and all components which are part of the playout path have to be able to deliver a frame in this particular rate. If they fail to do so, your program is going to show a blank screen. And this is very expensive for broadcasters and should be avoided at all costs. So, the second challenge is performance. Now, in my master thesis, I took the challenge to implement a working prototype of the graphics renderer. What that means is I started implementing a C++-based framework which provides the service of rendering broadcasting graphics. Once I have established the first working solution, I started measuring performance, analyzing and visualizing the performance traces, and continued to optimize this working prototype until it shows satisfying performance results. Now, why do we need performance in broadcasting? Well, as it is today, we render using Full HD, which has a resolution of 1920 x 1080 and is delivered at 25 Hz. Tomorrow, we might be confronted in broadcasting in UHD1, which is the successor TV format of Full HD. Now, UHD1 quadruples the resolution and at least doubles the frame rate. That means your broadcast renderer has to be able to process 8 times as much data as you would have when you render HD. So how did I implement it in my prototype? Well, I knew I had to take some input video frame, process it somehow, and write back the output frame with the graphics on top of it. Of course, I could use the CPU for that. CPU, the central processing unit, is a general purpose processor. You could do graphics with that as well. So, however, the image processing algorithms are very easy to be parallelized. As you can see here in the diagram, the CPU only has 4 physical cores, maybe 6, maybe more if you throw one in. But the GPU has more than 1,000 cores that you could use concurrently to render a single frame. Well, it's pretty obvious what I'm going to aim at. So the first research question in my master thesis is really how to take best advantage of the GPU when you want to render professional video formats. And there are a few things which you can read in my thesis about, which are not as easy and obvious to do when you work in the professional domain. Okay, this is great. We have the GPU with a lot of cores and it's very fast. But this has a price. And the price is that the GPU operates in a separate memory space, very often, than the CPU. So really what I needed to do first when implementing my prototype is to read the frame into main memory, upload it to video memory, which is done by a DMA controller, a very simple processor basically, which is then rendered by the GPU, again transferred back to main memory and played out through the output device. And you can see on the right-hand side of the slide, this is actually an actual execution diagram of my prototype. So this is actually captured data which is visualized. And you can see if you do that one after the other, that the processors, which are actually able to work concurrently, sit idle for quite a long time during this execution. At this point, I would like to quote Thomas True. He's senior applied engineer at NVIDIA. It's a very big graphics card vendor. And he's basically the person that consults very big broadcasting companies. So they call him and ask him to improve the performance of their renders. And he said a large part of the performance issue boils down to getting the data efficiently to the GPU. And it's not an easy process. Well, why is it not an easy process? What is difficult? The first, and this is probably the major difficulty, is that the problem goes back to your overall application design. So you have to be able to express the logic of the application in some way that allows easy parallelization of the execution. This is one way to do it. I will simplify it a little bit. And this basically shows the conceptual idea of the pipeline pattern as I implemented it in C++ in this particular framework. And it basically allows you to define separate stages which are able to run independently from each other and concurrently. And the data communication is achieved by sending tokens downstream through thread-safe FIFO queues. And something that's special about this approach is that you can send tokens also back upstream. The reason I need this complex infrastructure goes back to the way you have to deal with the graphics APIs. And once you start parallelizing things, you need to do a lot of complex synchronization. So what I was able to achieve is that the execution times are now actually overlapped. And you can see at this point that we perform 4 things at the same time. One frame is downloaded, the second frame is processed by the GPU, so rendered, the third frame is uploaded, and the fourth frame is read into main memory. Now this is much better. And to put these results into numbers, I would like to show you this graph. So this is basically the result that I started with. So my first implementation showed the throughput of 1.2 gigabytes per second. Now if you look at the necessary throughput when you broadcast UHD1, the new format, in real time, you would have to be able to achieve at least this amount of data per second. Now that's pretty close. It's actually too close. So you need a little bit more headroom if you want to implement it in a real-world working application. Using the overlapped parallelized approach, I was able to double the throughput. And these two graphs here actually use a pretty old graphics card. So if you use a newer graphics card, you could even achieve much better results. And this fits 3 UHD1 streams in real time on commodity hardware today. So I had the opportunity during my master thesis to work together with Tools & Air on this. Tools & Air is an Austrian-based company that basically develops software for the broadcasting market. And yeah, I'm very proud to say that they are going to use this framework in the future for their upcoming products. And I will be part of this process. I'm now working as a full-time engineer at Tools & Air. And I would also like to thank Walter Kunkner, who also came here today. Okay, thank you for listening. I would be happy to answer your questions.